of electromagnetic wave which was reflected from a conductor. And when it was reflected from this conductor, we observed a standing wave, or we call it the standing wave. And to perceive it better, it is good if we try to draw it. Wait a second. I got it. Normal incidence on a camera. Okay, so we got that the electric field, Zt, this was equal to AX, to incident electric field intensity, times sine beta 1Z, sine omega t, and then we got also for the magnetic field intensity, we get H Zt, this was equal to AY times 2 EI intensity divided by eta cosine beta 1Z cosine omega t. So this is what we get here for these two waves. And if we try to draw these two waves, we get the following. Let's assume that, so this is Z equal to 0. And since we have a standing wave, we obtain the following. We get that so a standing wave, this will be defined as a wave whose minima are fixed. Okay, so we will start, that means that if we have a 0 here at some time, this will always be a 0. And these waves will be static because a little later in time we are going to observe this wave, okay, or we're going to get also something like this. But in principle, these are nodes. They are nodes that are not going to move, and also the peaks. So we can say the following: peaks and nodes. Okay, and nodes are fixed in space. Okay, which means that if we sit here, we're never going to get to measure, let's say, a voltage of 5 volts per meter. But if it is a normal antenna, what we can do is that we stay here, we put a detector, and we always have the chance to scan the complete value of electric field as a function of time. But here, the peaks and nodes are fixed in space. So if we stay here, we're going to observe the maximum peak, then the peak will be decreasing because we have here the time propagation factor. And but this is, I believe, what we mean with the fixed standing wave. But now, if we see for a moment, I can ask you the following question: what is this? Is this the electric field or the magnetic field? What can you say here?
Doesn't it depend on what axis are we talking about?
Think about this one this way. Look at this. Sine beta 1Z. This value of the function, this is the boundary. So let's call it this is the conductor. So if this is the conductor at Z equal to 0, which one is 0?
Oh, sine 0, it's the electric intensity.
Electric field, that's true. But then the other component, it would be, so if we are to draw the magnetic field, we get here a maximum, which these are pi over 4 terms, okay? These are pi over 4. The 2 pi is here. So we go from here, we go here, we get this, this, and this. So the magnetic field intensity, so this is the H, okay? And why is the H? So it looks like H, when the Z is equal to 0, H is the maximum. So we can consider this is H max, which is equal to what? This is equal to 2 electric field incident divided by eta. Okay? And yeah, so this is how we can read this. And what about this amplitude here? This is 2ei0. But this is happening, right? It's not happening right at the boundary. So if we put a detector here that measures the magnetic field intensity, we get the maximum value here. We get further from the conductor, it will decrease, get a negative, minimum, and so on. And similarly, we also have this, and this, I think this is obvious. Here and here. So this is our standing wave. Yeah. And the next step, as the next example, we can. Lost this. Okay, so let's use the complete board. So this was the standing wave. I hope this is clear. We just have to keep in mind that, let's assume for a moment that an incident wave was a wave which is like this, ax times 5 e to the power minus j beta z. So let's look at this for a moment. And let the frequency be 100 megahertz. Okay? So if this is 100 megahertz, can we find the other parameters? So this is incident, okay? So if this is 100 megahertz, what is omega? It's 2 pi times 100 times 10 to the power 6, right? So this is the omega. And this is equal to what? We get 2 pi times 10 to the power 8. 2 pi times 10 to the power 8. This is omega. Then what is beta? How do we find beta? Can someone tell me the expression for beta? So this is beta. Or we can similarly say the beta is omega over c, and beta net would be equal to 2 pi times 10 to the power 8 divided by 3 times 10 to the power 8 again, right? This is the speed of light. What do we get? We get here that this beta is 2 pi over 3, right? And now, what is the wavelength? Can you check the expressions or the book for how do we find the wavelength?
Professor, 2pi epistolar beta.
That's correct. Thank you, Christina. So this is 2 pi over beta. So in this case, lambda is equal to 2 pi divided by 2 pi over 3. And this we get what? 3 meters. Okay. So we get a wavelength which is equal to 3 meters. Now, could we have found this differently? What do you think about the wavelength? So everything is okay here, okay? But could we have found this differently for the wavelength? What do we know? We know that, and let's not forget, we started with this information. We know that the speed of light is measured in what? Meter per second, right? So this is equal to the wavelength, which has a unit of in meters, times the frequency, which has units of 1 over seconds, right? Would you agree with this expression? So speed of light is always lambda times frequency. So if the speed of light is 3 times 10 to the power 8, this would be equal to lambda, which we don't know, times the frequency, which is 100 megahertz. This is 100 times 10 to the power 6, which means that we can cancel this out. And what is lambda? This is still 3, because this is the only term that remains. Okay, so what kind of questions we can ask here? So let's say that the next question will be the following. Find maximum electric field. What is the maximum electric field that is measured on this side of a conductor? Can you answer that? So we said it, it's twice the normal incident electric field vector, right? So what is the incident, wait a second.
Is it 5 in our case? And 2 times 5 is 10?
It's 10, because we said here, for standing wave, the amplitude of the wave is going to be 2 times 5 in this case. So the maximum would be 2 times 5. We're going to get equal to 10 volt per meter. Okay. The next question can be the following. Well, let's find out, so what is the H max? What is H in medium 1 maximum? We are not asking H1 or H incident max, right? H incident max would be the, how can I say, this 5 divided by the eta. And actually, let's try this one. We can say H incident max is equal to the amplitude of incident electric field amplitude divided by eta. What is this? What is this eta for vacuum?
377.
That's correct. 377. So this would be something like 500 times 1 over 100. So this is equal to approximately 5 divided by 3.4. This is 1.3. I'm not sure exactly, but 1.6 divided by 100. So this is equal to 0.016. Okay, so this would be the magnitude of this incident H max. Similarly, if we want to find out this other one, then this would be equal to 2 times this value, 0.016. 0.016. Now, the other question is we can ask the following. How far from the conductor do we measure 0 electron volt? Z is equal to what? So this is the question. Such that E is equal to 0 volt per meter. What can we see here? So we know it, it's right here, right? So how far is this? This distance, this is lambda, okay? Or similarly, maybe it's better if I draw it here. So the metra in meters, this is lambda. So how far is this from the conductor?
Lambda over 2.
That's correct. So we can say that the electric field is equal to 0 volt per meter at Z equal to minus 1.5 meters. Okay. Assuming that this was Z equal to 0 and Z positive is going this way, so the first minimum is at Z lambda over 2, which is, let me write it here, sorry for not writing it before. And then, or we can also ask, where is the magnetic field intensity equal to 0? It's going to be lambda over 4, right? It's going to be this distance. So H is equal to 0 and Z equal minus lambda over 4, okay? Which makes this, what's this, 1 over 5 divided by, this is 0.75, minus 0.75 meters. So these are some quantities which we can derive for the reflection of the electromagnetic field from a conductor. Do you have any more questions here?
Profesor, poate të fshis, se për kjo hëmaksi, tani, se ka mund gabim, sepse pash formunën, po nuk duhet të jetë pistim për eta, pistim për intrinsic impedance.
Here.
Jo, poshtë, kush ai zeti lart? Poshtë.
You mean this one?
Besoj kam fjalën një gjeti që fix aty. Po.
Okay, but this is also equal to this. So we found this H1 max. And you are correct. This would be equal to 2 times incident electric field intensity divided by eta. But this one, we consider this one as this quantity, right? So this would be 2 times, right? We found this maximum magnetic field intensity value. We found it here. I just substituted this value. Or we could do this one, 2 times 5 divided by 377. Is it clear?
Okay, faleminderit. Po.
Is it good? Okay, thanks for asking, because sometimes you skip something, but you should know. Okay, so try to make this experience as close to a classroom condition as possible, please. So asking questions is always good, but I think we did this calculation here. I just multiplied by 2 because we observed that this H max for medium 1 is also equal to 2 times H max for incident wave. Okay. So this is also like this. Okay, shall we move further? Okay, so the next step is we can consider a different case where we do not have incidence of a wave on a conductor, but we have lossless dielectric. What is a lossless dielectric? Or what is going to make it any different from this case? A lossless, this means that the sigma is equal to 0, right? So sigma is 0. So it looks like we have no attenuation. Okay, the wave, it is not going to diminish in intensity as it is propagating, right? Because it's not conductor, but it's a lossless dielectric. How? What is the index which determines some new properties which can be associated with dielectrics? Who can help me here? So what are these quantities? Epsilon r is different from 1, okay? So this is a lossless dielectric. So you have to look at these quantities, which means that epsilon is always equal to epsilon r times epsilon 0. And traditionally, this epsilon r is different from 1, but at the same time is larger than, how can I do this? It's larger than 1 most of the time, which means that this would be 51 times 8.85, I always forget this value, times 10 to the power minus 12, something, okay? So this is what we understand when we talk about a dielectric. Now, let's consider a similar situation, but let me see, probably I should use some other side to draw this. Let me do this here. So we have an incident wave, which is determined by Ki, incident vector. We have the electric field vector, which is Ei, incident electric field component. Then we have the reflected wave, which is coming backwards. This is Kr. This is the Er. Okay. And then we have also some transmitted wave component, which is Kt. Transmitted. This is K reflected, this is the K incident, then this is going this way, and let's write here the ET. Okay, so the first thing that we have to consider is this one, incident wave, transmitted, reflected. The second step is to identify the directions of the magnetic field intensity. Here, for the incident wave, what is the direction of the magnetic field intensity? It's pointing out of the board, like this, right? What about here? It's pointing into the board like this. What about here? It's pointing out of the board, we denote it like this. Okay? So this is H incident, this is H reflected, and here we have H transmitted. So we have these 3 components. Then we need to write carefully all the, let's consider, this is medium 1 and this is medium 2. What is the next step? We need to write down all the E and H, but we need to write a pair for incident, a pair for the reflected, and a pair for transmitted. So we go like this. Okay, so here we have incident wave. Incident wave. This is incident wave as a function of z. This is equal to ax times ei0 e to the power minus j beta 1 z. Okay, so this is the incident wave for the electric field. For the magnetic field, we get here AY, the incident electromagnetic field, electric field intensity divided by the intrinsic impedance with the same propagator, J1 beta z. We are propagating along the plus z, so here we get negative J beta 1 z. This is the first equation, this is the second. Then the reflected wave, which is the third equation, this we can write this one as ER as a function of z. This would be equal pointing AX times electric field reflected wave amplitude e to the power plus j beta 1 z. So we write this one beta 1 because we are in medium 1, we are on this side. So we can denote here we have beta 1, we have permittivity 1. On this side we have beta 2 and permittivity 2, which is going to be equal to ER times E0 for the permittivity. And similarly, we go ahead and we write for the fourth equation, this is the HR as a function of z. This would be equal to minus AY times a reflected wave electric field vector amplitude divided by eta 1 times e to the power plus j beta 1 z. This is the reflected wave. The third region, this is the transmitted wave, which we are going to write the fifth equation, where this wave is going to have the same direction as the first one, because it's pointing in this direction, and also the propagator is going to be very much similar. So here we have E transmitted wave as a function of z. This would be equal to AX ET0, the amplitude of the transmitted wave, e to the power minus j beta 2 z. Okay, so it is propagating along this positive z, but now we have the beta 2 instead of the beta 1. Similarly, the ht of z, this is equal to what? How did we denote this one? It looks like it's pointing out of the board. So again, this is x, this is y, and this is the z. Then here, it looks like the ht is equal to ay, so it's pointing out of the board, times e, this component, divided by eta 2 now, because we have the second medium, times e to the power minus j beta 2 z. Okay, so with all of these equations, what is the next step? So we wrote down all the relevant equations, but we have, so in the previous case, how many unknowns did we have in the previous case? When I say previous case, when you scattered a wave from a conductor, or when a wave was incident from a conductor. How many unknowns did we have? We had this was given, okay? And we had to find the amplitude of the reflected wave, right? So this, we had one unknown, so this was the question mark. Now in this case, we have given only one parameter, and we need to find what is the reflected wave amplitude and the transmitted wave amplitude. So how many unknowns do we have here? We have two unknowns, right? So this was a perfect conductor. In this case, we had also this transmitted wave, but we know this was equal to 0 in the case when we were sending a wave into a conductor, or the interface between two media. On one side it has a conductor. Now this is the second case. So we have two unknowns. How many equations do we need? How many equations do we need in order to answer, to find out what is going to happen after the wave hits the second median, we need two equations, and to do this, that means that we need two boundary conditions. What boundary condition can we construct in this case? Probably one of the boundary conditions would be the continuity of the electric field, and the other one would be the continuity of the magnetic field. So we're going to have the following. E1 tangent is going to be equal to E2 tangent, and similarly, H1 tangent would be equal to H2 tangent. So this means that when this, and then by the way, where is the tangent components? So if this is the interface with this paper I'm showing you, the tangent, this is tangent, okay? Electric field, this incident wave and this reflected wave, these are tangent, because if we draw it right here, this would be tangent. A normal component would be this, but it looks like the only vector here, which is normal to this interface, to this separation between the 2 medium 1 and 2, it's only these vectors. So these are normal vectors, right? So let me circle the components which are perpendicular to the separating interface. Which components are tangent to this separating interface, which we can draw this in a red like this. ER, this is tangent, this is tangent, and this is also tangent. Would you agree with this? And similarly, this is also tangent, this is, and this is. So it looks like we're going to have an easy job when we write down these equations. And what is going to simplify our task further is that, let me write it here, or better, I can use this part of the board. So we are going to have equation 1, let me do it like this. Equation 1 plus equation 3, this would be equal to equation 5. Okay? So we have this one plus this is equal to this, but we have to evaluate these at z equal to 0. And similarly, we have for the magnetic field intensities, we have the second equation plus the fourth equation. This would be equal to the sixth equation. And we evaluate these, all of them, at z equal to 0. Okay? Now, if we evaluate these at z equal to 0, what do you get for here? What is this term? What can you say? Any comment? So these terms, these exponentials at z equal to 0, they are equal to what?
1.
That's 1. Okay, so if they are equal to 1, does this problem, can this problem get any simpler? What do you think? What do you think this year? You answer this one. How can this problem get simpler? It cannot.
I couldn't hear what you said. Sorry.
It could be simpler only if they are 0, but they're not. But it is, I believe this is relatively easy, because now we have 1 plus 3 is equal to 5. And we have the following. We
can factor out E. No, we cannot.
No, we cannot, but we can do this. EI0 plus ER0, this is equal to ET0. We're talking about the amplitudes, okay? And then, this is what you get from the first equation. From the second equation, which means that we have to do the following. EI0 divided by eta1 plus, where is it? We have this, where we have actually, we have this expression that we do minus okay. So how many equations do we have here? We have 2, right? And we have 2 equations, 2 unknowns. So it is similar to, so how do we read this equation? This is something like this. ET0 minus ER0, this is equal to minus EI0. Then here we get ET0 divided by eta 2 plus ER0 divided by eta 1. This is equal to minus EI0 divided by eta 1. And I think this is simple because you can always solve this system, which looks like this. AX is equal to B, right? The coefficient matrix is a 2x2 matrix, and the unknown vector. So we have a 2x2 matrix, which you can easily write. This is the ET0 and ER0. These are the unknowns component, and here we have minus EI0 minus EI0 over eta 1. So we know these quantities because these are given, and we need to find these two components. With a 2x2 matrix with two unknowns, we can do a very good job. So here we get 1 minus 1 over eta 2 1 over eta 1. Okay. So since this is a simple system, you can also do the following. You can write here ER0 as a function of ET0 and EI0. Then you substitute the information into the second equation, and you can easily obtain the following relations. So what did we say? We said that we know EI0, right? And from here, we had to derive these, ET0 and E reflected 0. And in this case, where we can write the following, we can say that ER0, we get that this is equal to eta 2 minus eta 1 over eta 2 plus eta 1 times EI0. Then we can also write the following, ET0, this is equal to ET0, this is equal to 2 eta 2 plus eta 1 times EI0. Now, the first component, this is called so we can write this one as the reflection component, EI0, and this is equal to the transmission, which we write this with the tau, EI0. Okay. So, sorry, this is the reflection coefficient, and this is the transmission coefficient. Okay. So the reflection coefficient, this is defined as ER0 over EI0. So the reflection and the amplitude of the reflected wave divided by the amplitude of the incident wave, we get the reflection coefficient. The transmission coefficient is equal to the amplitude of the transmitted wave over the amplitude of the incident wave. So these are reflection and transmission. Reflection coefficient and transmission coefficient. Okay, then we can also write the following, that 1 plus the, probably we can erase this because I think we know how, we know what the bigger picture was. And here we can also write the following, 1 plus the reflection, 1 plus the reflection, this is equal to the transmission. Okay? And I believe we can easily see this because, so 1 plus this term would be equal to this second term in here. And when I say term, we mean the following. So we have this and this. Okay, and all of these we obtained it from these expressions that are written here on the board. Now, at this part, so what did we do so far? We just obtained what were what's the name? The reflection and the transmission, but we can always ask the following, so that's good. All we were given initially, it was this amplitude, the incident wave, right? Then we found this, What else can we find from this problem? What else can we find? We can find what is the electric field in region 1, okay? Because so initially, we sent this wave, which has also this associated magnetic field intensity, right? But then someone might also be interested into obtaining what is E1, okay? So, and what is E2? But this E2, this means that what is the electric field in the second medium? This one, in fact, is equal to the E transmitted. That's easy, okay? But what about the electric field in the first medium? This is, what is E1? Can you help me here? So, I think, given this, we easily derived what is the reflection coefficient. So we find this one as this component times EI0, okay? The transmitted one was the tau times EI0. Then, the complete electric field in medium 1 is going to be equal to the summation of this plus this, which in this case is going to be, where are these? Where is the incident and the reflection? So you do 1 plus 3. Okay, so in medium 1, let's also do it like this. I believe you can see this. This is medium 1, and this is for medium 2. Okay, so what is the electric field in medium 1? We just add up equation 1 and equation 3. So we can see here this is 1 plus 3, we got it, okay? And the same way, we can also find the following. We can get what is the H1. H1 would be equal to the H incident plus H reflected, which is equal to what? Equation 2 plus 4, right? So we have equation 2 plus equation 4. Okay? So this is what we get for this case. But then, once we add these, so I might need some space to add all of these. Let's use this part. So I believe this is relatively easy, right? So we said this is how we find the electric field, the magnetic field, by adding equations 1 and 3 for region 1. So let's take this out for a moment, and let's try to write the following. What is the E1? So let's do E1Z. This is equal to, we just need to add this term and this term, and we get, let's see what we obtain. So this is AX, it's there. Then we have EI, incident 0, e to the power minus j, beta 1z. So we can, so far, all we can factor is just the AX, right? What is this component here? What is this? Let me use this in double red lines. Let's get this expression from here. Okay? So let's obtain it from there. And this ER0, this would be equal to plus the reflection coefficient times EI0 times what? Wait a second, so this is not the line anyway. So let's put this here. E to the power plus j beta 1z. J beta 1z. Okay, we can factor out this again, and we get the following. We have AX, the direction is still the same. We can factor out the incident, the amplitude of the incident wave, times, in this part, what we can do, we can in fact even factor out, let's factor out also this term here. So we get e to the power minus j beta 1 z 1 plus eta. Then what should we write here? So E1 so this is going to be the expression for E1. And yes, okay. Let's see for a moment. Is it clear? So is it, this look good?
Professor, how did you obtain that e to the power 2j beta 1z?
I divided by this term, both sides.
But shouldn't it be with the minus, or am I wrong?
So I divided by e to the power minus j beta 1z because I took it out, right? So if I divide, so we get this, let's follow this for a second. This is j beta 1z divided by e to the power minus j beta 1z, okay? So if we divide it like this, then we get here 2j beta 1z. Okay, very good. Okay, thanks. Okay, so it looks like this is the complete electric field vector in one side of the medium, and then from here, I believe, yeah, this is all we can get, and we could also obtain what is the time-dependent. So the next step would be this, which would be then, this would be equal to the real part of this whole electric field E1z, e to the power j omega t. This is what we can then obtain for the electric field intensity. Instantaneous expression for the electric field. Okay. Then yes. Okay, do we have any question for so far, for what we did so far? One, let's see. In fact, now allow me to take this out for a moment. Even these, and if we look at these terms, we can write this one as, so E1z, we continue like this is AX times the amplitude, so let's write here E incident amplitude, the amplitude of incident wave, and then from this initial expression, we can, let me see how we derive this one. We can do the following. We can factor out 1 plus 1 reflection term, e to the power minus j beta 1z, minus the same term, e to the power minus j beta 1z, which means that this one actually is going to cancel this term, okay? And let me see, so I think we have the same thing so far, plus e to the power plus e to the power. So actually we're doing it. Let's assume that, so this expression, we can write it this way or this way. But before factoring out this term and taking it here, let's pick up the problem from this step, okay? And let's come here. So from this expression, what one can do is that we have this one, which is this term, and we are adding, actually maybe we can write it, I believe it's clear, but let's do it like this better. So we can write it like this. This is, we have factored out this term, we have e to the power minus j beta 1z, and then plus the reflection coefficient minus j beta 1z minus the reflection coefficient e to the power minus j beta 1z. So far we've done nothing new, okay? And then plus, now let's write this term now, okay? So we wrote the first term, we're good, we added, so these two add up to 0. So this should not disturb us yet, but we might use it to derive something. Then we have plus, we're left with this term, ei0 e to the power plus j beta 1 z. So all these terms are negative, this is plus, so because this is the transmitted component. And then we get here ax ei0, and then we observe here that we get 1 plus the reflection coefficient e to the power minus j beta 1z, okay? And then minus this term, this stays here the same, minus j beta 1z plus, let me think for a moment, okay. So e to the power j beta 1z, then this is equal to ax e, sorry, let's take another one. So this is the amplitude, incident amplitude 0, 1 plus the reflection coefficient. This is equal to tau. Okay, so we can write this one as the transmission coefficient tau, e to the power minus j beta 1z. Okay, plus here now we can use this expression. What is e to the power I theta minus e to the power minus I theta? What is this? I think we get sine, right? Like 2I sine theta. And you can check, of course, you can check this again. But for the last two terms, we can extract such an expression. So we get here plus gamma 2j sine beta 1z. Okay, so this is what we can, how we can simplify this a little further. And then from this expression, so this is the phasor, E1 as a function of z. Okay, this is actually as a function of z, because this is propagating along z. And from here, we can, now at this step, we apply this other step. So this is, we started from here, from this phasor. Let me get a refill. Let me get a pit stop. So we can get here now z as a function of time. This is equal to, so we keep multiplying it here by e to the power j omega t, right? Which you don't see it clearly, but now probably do. So we just multiply this term with these, And what we observe then is the following. We get AX times the amplitude times tau stands here. And what we are going to get here, this is e to the power j omega t minus this. What is the real part? It is cosine omega t minus beta z. This is cosine omega t minus beta z. And then plus minus 2 times reflection coefficient sine beta 1 z times sine omega t times sine omega t. Okay, we achieved it. So we had 1 and 3, we added them together, we got this phasor. Okay, this phasor, we just reformulated it and we got this other expression. It's exactly the same, but we just modified, we made it look a little different. And then we obtained the instantaneous expression of the electric field. Now, here, this term is a propagating term. So this is something that I wanted to come to. Propagating. Wave component, let's call it here. And this is a standing wave. So we noticed that when we had a pure conductor, so I believe we can erase this part because we just wrote this one to argue what we could get from this section here. So it looks like for the case of two mediums that there are lossless dielectrics, we get an answer which, different from the incidence on a perfect conductor, we have this propagating term as an extra term that appears. Okay, and So how can we go from this expression to the case of the what's the name? To the case of the perfect conductor? So I believe if we set this transmission coefficient equal to 0, which in the case of a conductor, it was really 0, so we have no doubt about that, because the electric field does not survive in a conductor, so it will converge to 0. So if we take this propagating term out, we're going to get an expression which was very similar or exactly the same with the case of a conductor. So it looks like if this is the propagating wave, where is this propagating wave propagating to? În ce thing poate să chevarea this propagating wave? Can you conclude something here? I believe if we look at this term, we might notice it. So this propagating term, where is it propagating to? So if we look at this propagator, which is obvious a little above, this is moving toward plus z-axis. So there is an effective wave propagation, or there is an effective energy transfer, which is carried by the wave, which is being, so the energy is transferred from z0 to z equal to 1, from z equal to 1 to z equal to 10, and along the direction, along the positive z-axis. Okay. So this is all we can discuss now regarding this special case of a wave that is incident on a lossless dielectric. Do you have any question? Anything? So everything is clear? Okay, so if you have no more questions,